Hello, here's some more waves practice questions. We're starting with state 2 properties which distinguish electromagnetic waves from other transverse waves. So let's go. First one, we'll say that they travel at, well, c equals 3 times 10 to the 8 meters per second in a vacuum. So that's one good thing. We could say that they are oscillating electric and magnetic fields, so E and B fields. You could say something to do with them being photons carrying energy, but I'm going to stick with those two. That seems fine. They've only asked for two and I'm happy with those. All right, part B, describe what is meant by a plane polarized wave. So plane polarized means that the oscillations are in a single direction. So that's one thing, but we also need to say that that direction is perpendicular to the direction of wave propagation. So I'll leave the word propagation out, but you could put that in if you're actually writing this out as a proper answer. But yeah, that's the two things you want to include then for a plane polarized wave. One direction, but that direction is perpendicular to the wave propagation. Right, second part of B, we've now got light from a filament lamp is viewed through two polarizing filters, shown in figure 6.1. Right, the arrow beside each filter indicates the transmission axis of that polarizing filter. Explain why the lamp cannot be seen by the eye. Right, okay, so they've put these two polarizers perpendicular to each other. So we can say, well, let's talk about each transmission one after the other. So light passing through polarizer 1, so I'll just call it 1 to save a bit of time, that's going to be vertically polarized. Then we can say, so that only light that is horizontally polarized, obviously write that out in full rather than using all this shorthand, will pass through polarizer 2, of which there isn't any. So therefore, no light reaches the eye. So it's just going through that step by step, what happens at each polarizer. Right, they're going to put that one in the middle now, aren't they? They always do this. This sort of question comes up quite a lot. They're going to put a third polarizing filter in between those two with its transmission axis at 45 degrees, because you always think, well, how can you get more light going through by putting another polarizer in the way? But you can. So explain whether or not any light reaches the eye through the filters. Right, so this time you will do, because so we can say after polarizer 1, we will get components of the vertical, so I'll just stick with that shorthand at the moment, components of the vertically polarized light at 45 degrees will pass through polarizer 3. And then we can say the same thing again, that those components, and similarly we can say that those what's passed through 3 after 3 components at 45 degrees, so this is now off to the side, will components of that will pass through polarizer 2. So we're now getting this chain. I mean, you could even draw these things out. So, well, we're going from having that to then having that to then having that. I mean, that is allowed, that you can rotate by up to 90 degrees in order to get some components that are passing through each filter. So, it's only that if you've got two consecutive filters that are perpendicular to each other that you will get no transmission. I mean, it might be even worth putting that in as a final bit. You only get 0 transmission if consecutive filters are perpendicular. Yeah, well, I'm not going to be able to write all that in, but yeah, consecutive filters are perpendicular. So it's probably worth putting that in as well. So you're going through step by step, but you can think you're always getting components. This is why you get the with Malice's law, isn't it, where you're looking at how the amplitude is changing. That if you've got something which is up and down, and then you take that 45 degrees component of it, so you're doing a cos 45 degrees, then you're going to be multiplying by 1 over root 2 on that. But the amplitude, well, the intensity is then related to the square of the amplitude, isn't it? So our intensity is going to halve. Our amplitude is dropping by 1 over root 2. So that's how you end up getting the Malice's law thing of the transmitted intensity is the incident intensity times the square of the cosine of the angle, because we're doing that cosine, but that's changing the amplitudes, and then we have to square that in order to get the change in the intensity. So that's where Malice's law is coming from, but we're doing that a couple of times going through this. So we're going to halve it when we go through the first one for intensity, and then we're going to halve it again as we go through the next one in terms of intensity. So we're going to end up with a quarter of the intensity coming through in order. So, I mean, that's another way that you could approach this whole question. They normally allow that on the mark schemes in order to quote Malice's law on this, and then just talk about these angles of transmission and what we've got here for theta. But I think it's nice to be able to see what's actually happening with these components when you're going through a polarizing filter, so that you're not just blindly using Malice's law. That you're seeing, oh yeah, we're taking that component and then we're squaring it because the components are amplitude, and then we're looking at intensity here. So yeah, that's quite a nice one to start on. The polarization questions are fairly tricky. So anyway, let's push on. So right, this looks like it's going to be standing waves, the old classic setup here, usually of microwaves. What we got, an estimation of the speed of electromagnetic waves can be made using the hotspots inside a microwave oven. Yes. Microwaves are emitted in all directions inside the metal walls of the oven at a frequency of that, causing stationary waves. And there's our hotspots. So they've marked the hotspots with X. These positions can be located to within a few millimeters by melting small areas of a bar of chocolate. Yeah, so yeah, you might have done this one in the lab at school, where you put a bar of chocolate in, or you can do it with marshmallows as well. You put a whole load of little marshmallows in, and some of them get absolutely fried, and some of them don't really do anything, which can be quite interesting to watch. Right, explain how a stationary microwave pattern is set up in the oven. Right, this is one of the standards where we've got this 3-step process that we wanted to go through here. So we're going to say that the microwaves are reflected at the walls. They've called them walls, haven't they? I think, yeah. Yes, metal walls. So reflected at walls. And then the reflected waves will superpose with incident waves. So again, you're getting all of the terminology in here. So you want to mention reflected and incident waves and superpose or interfere. And then you can say that produces a stationary wave or standing wave, whatever way you want to put it. Maybe go with what they've said in the question when they've gone stationary here. Stationary waves produces stationary waves. And then, say something about, that what a stationary wave is. So something like with a pattern of nodes and antinodes, with pattern of nodes and antinodes, because it also means you can get in some more terminology. And you think there's a lot of terminology we've now used in this. We've used reflected here, reflective waves, incident waves, superpose, stationary waves, nodes and antinodes. I mean, these are all key things they're going to be looking for on mark schemes. So it's good to get it all in if you can. Explain whether the points marked X on figure 7.1 are at nodes or antinodes in the wave pattern. Right, well, they said these are the hotspots. So this is where we're getting the energy. So they want us to explain. So X equals hotspot, and it is at antinodes where we have the energy. So antinodes as nodes have zero energy equals zero energy. Antinodes have maximum energy, and antinodes have maximum energy. So again, you're getting in as much terminology as you can. Right, so that was that. Figure 7.1 is drawn to half scale. Okay. But I don't think that matters because now I've resized everything on here. I mean, who knows? They've given us a scale off to the side here, so it doesn't really matter. By using measurements taken from the diagram, make an estimate of the speed c. Okay, make your reasoning clear. Right, this is going to be a little tricky. I mean, that's 4 centimeters. I mean, that looks as though it's about, I mean, going from there to there. I mean, obviously, I don't have a ruler here. It looks like about that. Should we say that's 6 centimeters? Let's say 6 centimeters. So 6 centimeters between antinodes. So that means that the wavelength will be 12 centimeters because half a wavelength goes between antinodes. So the C is going to be they've given us the frequency, haven't they? Yeah, frequency times wavelength. So that would be 2.5 times 10 to the 9 multiplied by 12 centimeters, so 0.12. So 12 times 2.5 is going to be 30. So that's sounding good. But then we would have nicked 2 off of there. So it'd be 30 times 10 to the 7, which is 3 times 10 to the 8. All right, that came out quite nicely. So yeah, there we go. That was not too bad. Quite a straightforward question in the end, that one. But yeah, make sure you're really slick on this bit of being able to write out without having to give it too much thought anymore of how standing waves are set up, because it comes up so often. Right, I'll do one more in this block then. So define the following terms as applied to wave motion: displacement and amplitude. Right, so displacement is the wrong sheet. Right, so displacement is the distance from the equilibrium point, of some point, of a point on the wave, at some time, because obviously the displacement is going to be varying around as that point is oscillating. So try to get, again, as many key points in as possible here. So we've talked about distance, equilibrium point, some point on a wave, and at some time. Right, the amplitude, right, amplitude's easier because we can just say the amplitude is the maximum displacement. So that is good. Now we've got frequency and phase difference. So frequency is frequency equals the number of oscillations per second or per unit time of a point on a wave. It's always useful to put in these things like, of a point of a wave. I mean, that's come up twice here, both for the displacement and for the frequency. And it's quite, it's just useful to have that, because at least you're talking about something in particular rather than just this completely abstracted idea of what a frequency is, of just saying, oh yeah, it's oscillations per second. Well, oscillations of what? Point on a wave. Right, phase difference. So our phase difference, that is so first of all, as soon as you get phase difference, because there's got to be a difference between two things, that's the only way you can get a difference. So you can say a phase difference between 2 points on a wave. So get that in straight away, and that makes it easier to write the rest of the sentence. So phase difference between 2 points on a wave, and that is how far through an oscillation one point is compared to the other. 1 point is compared to the other. See, if you hadn't have started off with the between 2 points on a wave bit, it makes it harder to write the second part of the question, the second part of the answer. So yeah, but these are all standard definitions that you want to have all these written down in a big list that you can just look through and keep refreshing your mind on these every now and again. And by the time you come around to exam time, it's just nailed, isn't it? embedded in your mind. Right, we've now got some wave profile going on here in part B. Figure 6.1 shows a transverse pulse on a slinky, an open wound spring at time t equals 0. The pulse is travelling at a speed 0.5 meters per second. They've put that on there from left to right. They've put that on there. The front of the pulse is at point X, 0.25 meters from point P. Okay, right, so they've marked on all these distances. On figure 6.2, draw a displacement Y against time t graph for the motion of point P. Oh, so the wave's moving along. P's going to be following this wave shape as the pulse goes past, and they want us to draw it out. Right, so it's going in blocks of, if it's moving at 0.5 meters per second, and these are in 0.25 meters, each block of this is going to be in half-second blocks. So for the first half a second, nothing is going to happen at P. It's just going to be flat, completely flat. Then we're going to get this first pulse, which is going up to 0.2 meters amplitude, is going to come through, and that will last half a second. So we want to try and draw that out as smoothly as we can up to 0.2 and then down again. I mean, you want the peak right in the middle. Mine's gone a little bit lopsided, but you want to try and get the peak in the middle. So that's dealt with that bit. Now we've got the bit where it's going below down to 0.12. Right, let's actually mark the midpoint. Oh my word, right, okay, there's too many lines here for me to tell exactly where 0.12 is. My eyes are just going funny, but let's say it's about there. So you do that for the next half second, then we're going to 0.08. So somewhere around here or something. Again, it's quite hard to tell with these lines. It just gives me double vision. So that gives you the last bit, and then we go flat again at the end. So we're trying to draw out, essentially you're drawing out this profile of the slinky, but in reverse. And, you know, making sure that you're hitting the right amplitudes on all of these. But, you know, you want to get that trough there at 0. or minus 0.12. You want to have this peak at 0.08. You want to have this peak at 0.2. So that's what we're aiming for, and you want to get them all at the midpoints of these half-second chunks. So I've done the best that I can drawing on this screen, but you get the idea. So that was a quick question to finish off on, but I'm going to leave those there. There's quite a nice range, really. We had standing waves, polarized waves, pulse going along a coil. So yeah, nice bunch. I'll be back with some more in the next video.